this okay? Yeah. Okay, good morning, students. Good morning. Good morning, everyone. Happy Monday to you all. I want to believe you are ready for the class. We just want to request that you give us about 2-3 minutes to sort out some technical issues. We are live. Thank you. Okay. Should be. Okay, good morning once again, dear students. You are welcome to CHM 101 class. I believe you had a good weekend. We are starting right away, and I believe that you can hear me. Good morning. I hope you can hear me. Some are saying we can't hear anything from here. I believe you can hear me now. Can you? Please let me know you can hear me. Oh, good. At least I have a confirmation that you can hear me. So we are going to continue our classes, still on thermochemistry. We are going to start another subtopic. You will recall that last Friday we talked about the various types of attractive forces, and we also began to look into the issue of order, because as you increase the kinetic energy of a system, you increase the entropy. So let's look at what happens in a system in terms of entropy. You are all familiar with entropy, but it's still good you are reminded that entropy is actually a thermodynamic function, and it measures the degree of randomness or disorder in a system. It's usually denoted as S, and the unit is joule per kilo per mole. That is for any substance. For any substance, you find the entropy term having the unit of joule per kilo per mole. I mean, joule per Kelvin per mole, sorry. So entropy is a state function. And I hope you know what we mean by a state function. I've tried to put it here, that is a property whose value does not depend on the path taken to reach the specific value. That is the state function. So if you have to move from one state to another and the path is not so important, then that property is a state function. And when we talk about an extensive property, that's a property that depends on the amount of matter. So these are properties that they change depending on the concentration or number of moles, generally as the amount of matter changes. And so when you are talking about the second law of thermodynamics, you are all familiar with the first law. The first law is the law of conservation of energy, that you can neither create you cannot create matter. Now, but you can transform it from one form to another. Now, if you look at the second law of thermodynamics, it generally points to the fact that a system will naturally tend to higher degree of disorderliness. So if you leave it over time, anything you put down is going to increase this entropy. And so as we increase the entropy, we are saying that the disorderliness is increasing. So the degree of randomness can be measured using the term entropy. That is what we mean. And as you increase the energy of a system, you increase the entropy. And if entropy is increasing, it also means that disorderliness is increasing. And that is why we say generally that the greater the randomness, the higher the entropy, especially if you move from a solid state through liquid state, through gaseous state. We discussed the changes about all of these states in the previous class. So it then means that a gaseous system has much greater disorder than liquid system, which of course we have a greater disorder compared to gases. So what then do we need to understand in determining the direction of change in entropy? You may have a solid changing to liquid and then to gas. For example, using water, which is a very common solvent, you can have a lump of ice changing to liquid, which implies that the ice has absorbed heat from the surrounding, and thus it has increased its disorderliness, which means that the amount of energy has increased. So when you have such change or states, you can determine the change in entropy. And so change in entropy is going to be S of product, that is the entropy of the product minus the entropy of the reactant. So the other thing you need to do is to know that you can have a system that is changing from an initial state to a final state. So that initial state is similar to what we used as S for reactant here. and the final state is more or less what is similar to the product. So when you have the final state having greater entropy than the reactant state, the difference is going to give you a positive value. So we say that change in entropy is positive. And when you have the reverse, you say that change in entropy is negative. Of course, positive entropy also has this implication, which means that the system or the reaction is spontaneous. So you can have change of states when you have a substance. There are, let me say, there are three main categories that will be considered where you can see where you can think or determine the direction of entropy for a system. If you have a change of state, for instance, when you have a substance that is changing to a state of higher energy, definitely in such a situation, the entropy of the system will be positive because the product side is having a higher amount of energy than the reactant side. Excuse me, let me go back. Let me go back a little. So the change that is associated when you have a substance move to a higher energy, like we demonstrated as we move from solid to liquid and then to gas, the entropy is going to increase. But if the change is to a lower energy state, then you're going to have a negative entropy. For instance, if you have water in liquid states, this is water in liquid states, and it's changing to water in gaseous states, definitely you are increasing the degree of disorderliness. You are increasing disorder in that system, and delta S is positive because the S entropy here will be larger than the entropy here. And so if you go back to the equation that we gave, then you will see that S for the product is going to be larger. I hope I'll be able to scribble some things on the screen as we go on. For now, I'm still trying to get used to the new writing. Right. So, okay. All right. We will get there. So where we are now is to see that H2O in gaseous states. If you recall what I discussed with you in balancing the intermolecular forces, you see that the molecules can be so free apart. And of course, that speaks about how large the entropy can be. But for water that flows together, the entropy will be much lesser. So the molecules in that diagram that I showed you earlier on, they are closer together. And you will agree with me that the degree of disorderliness for a system of this nature will be larger than the degree of disorderliness for the system of this nature. So you're going to have the change of states from liquid to gas will give you positive entropy. And like I said earlier on, that implies that the entropy change that is positive indicates spontaneity. So that means the system will occur, the process will occur on its own without adding any external amount of energy. Now, if you look at a normal melting point or boiling point of a substance, we are going to consider two states. The states in which it's going to exist as a solid before it melts, and then when it melts, it's going to be in a different state, which is liquid. And so at normal melting point or boiling point of a substance, the two states of the matter present at temperature and 1 atmosphere, they are in equilibrium. So there is a point in which both solid and liquid will exist together. And that equilibrium point is also very vital for us. So delta S can be determined because under such a condition, you find that delta G minus delta A, equals delta H minus T delta S, which you are very familiar with for free energy. At equilibrium, that will be 0. And so if that is 0, then you can see that the delta, if this is 0, then it means that this will be equal to this. And if both of them are equal, then this expression will hold. Because the change of state from from solid to liquid is reversible. Because it's reversible, the delta S for the change of state from solid to liquid will be delta H fusion over temperature. Temperature in this case is the melting point in Kelvin. And if you have a change from liquid to gas at the boiling point, which is the temperature at which that change occurs, the transition means that there will be a point where you have an equilibrium in the course of transitioning from from liquid to gas. So delta S is going to be delta H of vaporization over temperature at boiling points, using this same equation that I showed you earlier on. And so if you want to reverse, for instance, if you are reversing, let's say you are moving from liquid to solid, that means that there is condensation. There is a condensation. If you are moving from gas to liquid, there will be condensation, and the sign on delta H of vaporization will change to the opposite sign. So that is how they are related when you are talking about equilibrium expression to determine delta S. So let's move on to the second type, that is decomposition or composition. For decomposition or composition, just as the name implies, we have to ask ourselves, what is happening? What is happening in this system? So before I go on to this second one, I want to share the first attendance code. First attendance code, please take notes. The first attendance code is 766 XE. Figure 7, figure 6, figure 6. X in capital letter, uppercase, for xylophone, E for energy. So 766 XE. Please take notes and register your attendance. You don't have to share it. 766 XE. 766 XE. XE, there is no point typing this. Everybody who is in the class should have the code, except you have an ulterior motive. We have said it again and again that you don't share the code. Thank you. I want to believe that you have submitted your attendance code, so I'm going to continue now. So the second important change that we can consider is decomposition or composition. From decomposition, we know it means breaking down of a substance into smaller molecules or smaller particles. Composition means bringing together to compose, to make different substances or molecules to come together to form a single substance. And so when you are breaking down any substance, you are decomposing it. It means you are moving from, say, 1 mole to more than 1 mole. So you are simply increasing the entropy because you are breaking it down. You are making them to become smaller, to become freer. And so you increase entropy, and so delta S is positive. But if you are bringing them together, of course, that requires some energy. And that means that the entropy change is going to be negative. So if you consider calcium carbonate, for instance, if you break it down to calcium oxide and CO2, if you examine the molecules, you'll find out that 1 mole of CaCO3 is breaking down to 1 mole of CaO and CO2. And one of these substances is also in gaseous state, which tells us that entropy must be very much larger than what you have in calcium carbonate, where all you have is solid. So solid here, and you can see there is a gas here, and that means delta S is positive. In the second example, you can see nitrogen, 1 mole of nitrogen, 3 moles of hydrogen, forming 2 moles of NH3. Interestingly, this is a homogeneous phase reaction. All of them are gases, but one thing is clear: there's 1 mole here, there is 3 mole here, and because there are 3 moles and 2 moles, and 1 mole, that means the total on the reactant side will be 4 moles. All of them are in the same state, and that is how you consider the change in entropy. Here you have 2 moles of the product form. So if 4 moles is giving you 2 moles, that is a composition. That is a composition, and so delta S is negative. You are bringing more order into the system. So 4 different moles or substances are compressed into 2. So that is a negative delta S. If you look at the third one, you have 2 moles of a solid substance, giving you 1 mole of a gas here, 1 mole of another gas here. Interestingly, the total number of moles is 2 on the product side and on the reactant side, but they have different states. And because they are in different states, this is solid and this is gas. 2 moles now in gaseous state will give higher disorderliness on the product side than on the reactant side. So when you take the difference, you find that delta S is positive. So that's a spontaneous process. Having said that, the third one is change in volume occupied. Change in volume occupied. For change in volume occupied, it's also very simple to understand. When you have a gaseous substance decompose into another gaseous substance of smaller volume, entropy will decrease. But entropy will increase if you have a product that is of higher volume. Unfortunately, this sign is not showing, but this is just to show the product that is formed. N2O4 is a gas, and NO2 is a gas. But here you have 2 moles of this gas and you have 1 mole of this gas. So the volume change from 1 mole in N2O4, if you consider it in terms of volume, is going to be 1 volume to 2 volumes of NO2 for the forward reaction. So you're going to have the entropy change to be positive, because here you have 2 moles, and in terms of volume, this is larger. Volume is directly related to number of moles. So this is having larger volume than this, and so delta S is positive. But if you reverse the process this way, if you give us the reversed reaction, you are going to have delta S to be negative. So in summary, what we are saying is that the entropy change involved when a system changes from an orderly state to a disorderly state is always positive, and that indicates spontaneity. And so from a disorderly state to an orderly state, entropy is always negative. I think I explained that enough, and I want to believe you understand, but if you have any question, you will ask me later. So still talking about entropy change, there are some changes that we must acknowledge they take place. And that takes me back to the second law of thermodynamics. As I stated earlier on, a system will tend naturally to higher entropy. So what we're saying is this: for instance, if you leave anything, and just anything, you leave it without using it, it's going to break down. It's just a matter of time. No matter how good, how beautiful that thing is, even your devices that you use, anything you place in an environment, over time, you're going to find it to be breaking down. That is, it's going to be tending to increase the entropy. That is the law of nature. If you leave food unattended within the surrounding, you will find out that with time, it's going to break down. It's going to decompose. If you leave anything like water, for instance, you leave it without applying it, just leave it in the environment, you find out that over time, it's just going to increase its entropy and change its state from, if it is solid, to become liquid, or if it is liquid, it just disappears. You find out that, oh, this drop of water that was left on the table has disappeared. It is because that law, second law of thermodynamics, takes effect universally. So things tend, or systems tend to increase in entropy. Even the disorderliness is seen in the world around us. So when we talk about a universe in thermodynamics, what are we referring to? We are referring to the system and its surroundings. So the universe is system plus surroundings. And what do we mean by system? So if you want to carry out a reaction, you will put it in a reaction vessel like we have here. This reaction vessel is the system. Everything in it, that is where the process or change in chemical process is taking place. That itself is the system. However, everything else around it is the surrounding. So in the course of time, you will find out that energy can flow into that system or energy can flow out, depending on the environment or the surrounding that you create for that universe. So bear in mind that the entropy of the universe is always equal to the sum of the entropy of the system and entropy of the surrounding. So if you have the entropy of the universe as positive, what it tells you is that delta S of system must be positive, and this also must be positive, or whichever way, maybe this is smaller and this is larger, but both are positive. At the end of the day, whichever combination you have, delta S of the universe being positive implies that the entropy of the universe increases. So this is similar to what we have been discussing about entropy generally, and it means spontaneity. And if delta S of the universe, depending on how you have them, the system and the environment, which is the surrounding, combined, for delta S negative, that of the universe is going to be said to be non-spontaneous. But if you reverse it, it's going to be spontaneous. However, you can also have delta S of the universe to be equal to 0. In that case, we say the process is spontaneous, but it has no tendency to occur. The system is at equilibrium. So, how do we make use of this knowledge? When you have a system in an environment, you have to talk about the delta S universe. But the delta S of the surrounding is very crucial in determining what happens to the system. So for entropy change in the surrounding, there are things you must consider, majorly 2 things. You are going to consider the sign of delta S of the surrounding, which will depend on the direction of heat flow. So if heat is flowing out of the surrounding, okay, it means it's flowing into the system. And you will also consider the magnitude. And these are what plays out in that expression that we put earlier on as delta S of the universe being equal to delta S of the system plus delta S of the surrounding. So once you understand that, you will be able to see what we mean by this. So for an exothermic process, delta S of the surrounding is positive, always positive. That means the system is receiving heat. Is losing heat to the surrounding. So delta S is positive. And then for an endothermic process, it means the system is taking heat from the surrounding. Okay, so the delta S of the surrounding is going to be negative. So for a reaction taking place under constant temperature and pressure, you must bear in mind that delta S of the surrounding is minus delta H over T, which means that spontaneity, that is the implication, spontaneity depends on temperature. Spontaneity will always depend on temperature. So, having established that, we can determine delta S of the universe from delta S of the system and delta S of the surrounding. And like I said earlier on, this is the table that summarizes it. How do we have a spontaneous system? When delta S of the system is positive, delta S of the surrounding is positive, delta S of the universe is going to be positive. And delta S of the universe being positive means spontaneity. It's not the delta S of the system alone or the delta S of the surrounding. It is the delta S of the universe. The value, the sign, we determine the direction, we also determine whether it's going to be spontaneous or not, whether it's not spontaneous but has the tendency to occur. So if you look at all of this combination, you will agree with me that this is the equation that describes it. For example, in the last one here, I said if delta S of the system is negative and delta S of the surrounding is positive, by the time you sum the two, it can be positive, it can be negative, but it will be spontaneous. The process will be spontaneous if delta S of the surrounding has larger value than delta S of the system. This is simple to comprehend. So for a reaction, maybe not just the system now, for a reaction, we also apply change in entropy, and that means that we will consider the reactants and then consider the products. In this case, you need to know the balanced chemical equation for that reaction. And so the summation of the entropy of all of the molecules in that system on the product side minus the summation of all of the entropy of all the moles of substances present on the reactant side will give you the delta S for the reaction. So delta S, this is delta S for reaction, if I can put R there. So for reaction, that is what you have. And if your reaction is taking place, if the reaction is taking place under standard conditions, then you have to put the standard conditions for the entropies of the reactants and that of the products. So you must note that N and N here, they are coefficients of the substances in the products and reactants respectively. So N is for products and M is for stoichiometry of the reactants. This is very important. I want to take an example for us to see. In this example, we can see practical application of what we're saying. So the question says, calculate delta S for the reduction of aluminum oxide by hydrogen gas. It's possible that you have this question without a balanced chemical equation, but to simplify your job, the question has a balanced chemical equation. If that is not balanced, if it's just written without balancing the stoichiometry, for example, you may not have all of this there. It's your job to balance it. So, but interestingly, this is well balanced, but we can quickly examine it. The question again says calculate delta S standard for the reduction of aluminum oxide by hydrogen gas following the equation given there. Given that delta S, given that standard entropy for aluminum oxide, hydrogen gas, aluminum solid, H2O, they are all given respectively. So it means that this is for this and this is for this, and so you can readily substitute the values. So if you examine that equation of reaction, you will see that it's balanced so as not to waste our time. And so the solution is you come here and look at the first thing is that this is a standard state. You must bear that in mind. And so delta S here will involve the summation of all of the entropies of the reactants and all of the entropies of the product. So if this is product minus what you have for all the reactants in standard state. And that is what we have here. So if you look at the number of moles on the product side, which is where we are starting from, on the product side, we have 2 moles of aluminum in solid state. And we know this is for aluminum. So we come here and substitute the value in joules per Kelvin per mole, because that is for the substance. And so you do the substitution for all of them, and then you will find out that this will cancel out in each one of them. This cancels out. And so at the end of the day, you will find the value for all of the products. There are 2 products, H2O and aluminum solid. This is what you have. Okay. And that's the value. You can determine it from here to here. So 2 moles of aluminum and 3 moles of H2O must reflect in your calculation for you to get it correctly. And then for the reactants, you have all of this, and you have 1 mole of aluminum oxide and then 3 moles of H2 gas. So if you do your calculation correctly, you will obtain 179 joule per Kelvin. So that is a good example for you. And if you have a system that has a positive value like this, the question can be taken further, because this is definitely a positive value, even though we have not put positive sign there. You can be asked further, what do you say of this reaction? Is this spontaneous, non-spontaneous, or whatever? So you should be able to answer. In this case, what you have is a positive entropy and definitely a spontaneous reaction. So let's talk about free energy. Free energy changes. You know about free energy is also a thermodynamic function, but it's related to entropy. So we are looking at entropy as it relates to free energy. You know generally from your O levels that G is equals to H minus T delta S, where H is enthalpy and T is temperature, S is entropy. Free energy, called Gibbs free energy, is named after the scientists who developed that kind of measurement. But you must not forget that every chemical reaction involves a change in free energy. And that change is delta G. So the change in free energy can be calculated for any system that undergoes a change, such as a chemical reaction. To calculate it, you are very familiar with this expression. You are so used to it. Delta G is equals to delta H minus T delta S. And if the reaction is occurring in standard state, then you have to include the standard enthalpy and entropy for the delta H to be in standard state. How does this relate to spontaneity? The Gibbs free energy depends on the initial and final state of the system. That is also the same as what we have for entropy. So you can determine delta H based on free energy of the reactant and free energy of the product. Again, that of the product comes first because it's the difference between the final state and the initial state, like we have for entropy. So for any chemical reaction, in the same way we calculated delta S, bringing into mind the stoichiometry of the balanced equation of reaction, you have to factor that for the products and for the reactant. So delta G is going to be summation of all of the free energies of the system for the total number of molecules that are there, and then that will determine how you obtain your value. So when you have delta G equals negative, just like you have for certain substances, for reactions too, it will mean that the reaction is spontaneous, which means it occurs as it is written. For G, delta G equals 0 is at equilibrium. So the two phases are in equilibrium. There's no useful work. There's no free energy to work. And then delta G equals positive means that the reaction is not spontaneous. which means the reaction cannot do any work. So, for example, if you have delta G to be negative for T equals 273.16 Kelvin, that is indicating spontaneity. That is, the reaction is spontaneous. For example, in the case of ice, at T greater than 273, that is 25 degrees Celsius, you will see that ice will change to water. And delta G is positive for less. When you have less temperature is less than that value, you will find freezing will take place. And under standard conditions, which implies 25 degrees Celsius and 1 atmosphere pressure, you will use delta G in standard states. However, you must take note that free energy of formation of an element in a standard state is 0. This is what we are saying. Formation of an element. When you are looking at an element in the course of any reaction, the delta G implies the delta G of formation of that element, just as it implies delta G of formation of the substance that you are considering. So when you have an element, you are not forming it, it occurs naturally, and in a standard state, it is always 0. You must bear that in mind. I will give you examples to help you relate better to that. So how do we estimate delta G? Using that same equation, bearing in mind that at low temperature, T delta S will become very small. So if T is small, T delta S can become very small, and then it means that the system or the reaction is enthalpy driven. So delta H controls the system or controls the reaction. So such is what you have for exothermic reaction that are, because they are feasible at low temperature. And at high temperatures, T delta S will become very large, and that becomes more important. If this is very large, if this term is very large, then it means that you can have delta G to be negative. And at high temperatures, that is going to happen. And for an endothermic reaction, delta S must be large enough for delta G to be negative. So you look at T delta S as very important. Then for you to have a negative delta G, it must be that delta S is large enough. If the reaction is endothermic, that is, if the reaction is taking in heat from its surrounding. And then for exothermic reaction, it can become explosive because endothermic reaction is taking in heat and is favorable at high temperature. So reactions that have negative delta G are hexagonic reactions, which means energy is existing in the system on its own, irrespective of the surrounding. And if a chemical reaction occurs and it requires an input of energy rather than releasing energy, we know that delta G is going to be positive. So this kind of chemical reactions are called endergonic reactions. They are non-spontaneous. So how do we also apply this? Spontaneity and non-spontaneity of of a reaction, like you said, depends on delta G value. So this table summarizes what to expect. If delta G is equal to delta H minus T delta S, then the signs of delta H and delta S are important. And don't forget temperature. In some cases, you will find T delta S being considered there, so the sign may be different. But I already explained that in the previous slide, and that is why I'm not using that table here. What we are concentrating on is delta S value and delta H value. And this explains what you should expect. When you have delta H as negative and delta S as positive, delta G will always be negative, and that means the reaction will always be spontaneous. And if you have the reverse, it's never spontaneous, then those ones that are in between will depend so much on the temperature of the system. Okay, so I haven't said that Let's look at an example here. This question says you should determine the free energy change for the reaction given here at 25 degrees Celsius. So this is formation of ammonia from nitrogen and hydrogen. And you are given the delta H and delta S. The question is determine the standard free energy change for the reaction. So the equation delta G equals delta H minus T delta S is all that you need to use. So this is not A. So if you have that, your job is simple. Substitute the values because, interestingly, this is also a balanced chemical reaction. So because that is balanced, you only need to substitute for delta H in this equation, and this is delta H in kilojoules. You also have to bear in mind the units of these parameters. And the temperature is said to be 25 degrees Celsius. 25 degrees Celsius, that's 273.15 plus 25. So you must convert it to Kelvin because the unit of this will matter. Delta S is in kilojoule per Kelvin, sorry. So if you look at this, some of these units will cancel out. You will end up with minus 25.178 kilojoule. So that is the answer. You can try it and let me know if you get the same value. Now, our time has gone a bit. I'm going to give the second code for you now. Please get ready for the second code, attendance code. So I'm sharing the second code. Second attendance code 67 HKG, all in upper cases. 67 H for hand, K for kilos, and G for gram. 67 HKG. 67 HKG. So we have to continue. I want to believe you have entered your attendance code. And before I continue, let me make this announcement. I'll still make it again. For those who are waiting online to join Physics 101 lecture, please be informed that Physics 101 lecture will not hold today. You should be informed so you can use your time for some other meaningful things. Physics 101 lecture will not hold today. So let's look at another example. You are to show that the reaction CO plus half mole of oxygen to give CO2 at 300 Kelvin is spontaneous. The standard gives free energies of formation of CO2 and CO are given respectively. So the first thing to do is to check, is the equation balanced? And apparently this is a balanced chemical equation. And so you start with the products, you get the summation of the free energies, and then you look at that of the reactants, you take the difference, just the same way we did for entropy change earlier on. So delta G of the reaction, actually this should have an N and M term. Please bear that in mind. And for this system, CO2 is involved. Let's look at the molecules or the substances that are involved. We have H2, we have O2, we have CO2, and we have CO. Oxygen is in a standard state. We have free energy of 0 because that is the state at which it occurs naturally. And so here, half of the Gibbs free energy is going to be represented as 0, and that is how you solve this problem. So delta G of the reaction is going to be this, which is for the product CO2. CO2 is already given here. And then this is for the reactant. The second reactant has the value of 0. So delta G of the reaction is going to be minus 257.2 kilojoule per mole. Minus 257.2 kilojoule per mole, which implies that at the given temperature, delta G of the reaction is negative, and so the reaction is spontaneous. So that is how you solve the problem. There's another function which we must not but talk about, which we must not fail to talk about, and that is enthalpy. Enthalpy is expressed as H equals U plus PV, where U means the internal energy, P is pressure, and V is volume. So when you have a process that occurs at constant pressure, the heat flow can be heat released or heat absorbed for the process, and is equal to the change in enthalpy. So if we use Q to represent heat, whether it's heat flow that is released or heat flow that is absorbed, delta H means Q, or Q means delta H. So we use Q a lot. And enthalpy is a state function. I explained what a state function is earlier, and it depends entirely on the state functions of temperature, pressure, and internal energy. So the unit of molar enthalpy, bear in mind this is molar enthalpy. If it is not per mole, if it is not for 1 mole of the substance, it will not have per mole units. It's simply heat, which will be in joules. But for a molar substance, molar enthalpy is used, and that is joule per mole. So what about enthalpy changes? This is just a simple reminder of what you know already, but we are going to remind you or refresh your memory before we go on to discuss the newer things. So you express enthalpy as a change in enthalpy for a process. So we are not going to talk about for a process, we are not going to say enthalpy of the process. It's going to be change in enthalpy because it has involved change of states from one state to another. So the start phase or state is the initial state, and where it stops or where the process ends is the final state. So change in enthalpy, delta H is used, and it means change in heat of the system. Don't forget that I said heat can be expressed as Q. So for a system or for a reaction, delta H is H for the final state minus H for the initial state. And for a chemical process is H of the product minus H of the reactant. And so when a system or a reaction loses heat to the surrounding, we say that the reaction is exothermic, that you know of, and delta H is negative. And it implies that delta H of the product is actually less than delta H of the reactant. And that is what you see in an exothermic process here, where the heat and potential energy are similar, or they have direct correlation. And so the initial here is at this point, and the product is at a lower value. So if you look at that, the amount of heat released is expressed in terms of the difference between what you have for the initial and the final. And so you can see that delta H of the product here is smaller than the delta H of the reactants. I'm sure you are used to this and potential energy diagram for an exothermic reaction. So if you measure the reaction progress, the amount of heat involved at the start of the reaction is higher than the amount of heat that you are left with at the end of the reaction. So that is an exothermic reaction. And for an endothermic system, this means that the energy of the initial state, that is the reactant state, is much lower than the energy of the final state. So bear that in mind, and that means that delta H of product is greater than delta H of the reactant. So I have just 5 minutes left. I think I will want to stop here. Let me give the last code and let me see if you have any question so that we will be sure that everybody understands what we are teaching. The last code for the day, please take note, is 48 GPJ. Figure 4, figure 8, G for goal, P for product, J for joule. 48 GPJ. I don't know if you have any question. You are free to ask me your question, but don't forget that Physics 101 class has been cancelled for today. It will not hold. I think some people are so used to sharing this code. I don't know what they intend to gain. So if you have any question, please feel free to ask me. I don't know if there's any question that has been posted here. Oh, they are saying the attendance site is down, ma. Please let me know if you have been able to. Is okay. Okay, people are submitting the attendance code. Maybe it has to do with the problem at your end. Somebody is asking, how is oxygen? Oh, I don't understand that question. Oxygen gas is O2. The element oxygen is represented with letter O or designated letter O. That question is not clear to me. You have not made your question clear. If you have any question, you should ask now. And if you need to make your question clearer on that oxygen question, please do that. Yes, this part of the course, thermochemistry, will not come out in the exam. Somebody is asking the test. Sorry, in the test, you are not going to be asked questions on thermochemistry. Please note that. Somebody is still saying, I'm unable to assign attendance. Please check your network. There is question already. I don't understand what that person means. The second example is not clear. The second example given for which of them? Because I gave 2 examples for one of the terms, and I gave 2 for another. So I need to know which of them you are referring to. Please make your question clearer to me. My time is almost up. What is the main difference between entropy and enthalpy? Okay, entropy is a measure of disorderliness. Enthalpy is a measure of amount of energy. I think that is simple enough. So enthalpy is about energy, entropy is about disorderliness. Second example, for enthalpy or for Gibbs-free energy, or for which one? I still don't get that question. The second example, for which one? This topic is not coming out in the test. In what condition is the entropy not spontaneous? Please check the table. You can always go back to, the second we treated is not clear. Do you mean the text? Because I used it in form of image. Please, you can watch it again online. Thank you for that attempt, Oluwadara Angel. A state function is already defined for you in that note. If you were in the class, you will know. I said a state function is that function that does not depend on the path that the system is taking. It's just about the initial and the final state. So the path taking is not does not affect it. Yes, the attendance link is working. Please check and be sure your network is not the problem. State function is already defined. If you were with me, you will say I even wrote it out. State function is defined here. Property whose value doesn't depend on the path taken to reach that specific value. That is the state function. It's in the notes under entropy. And I told you that enthalpy too is a state function. So all of this you can check. How is delta G of oxygen 0? Is in a standard state. That is what you need to know. Oxygen is in a standard state. Oxygen is in a standard state. So it is 0 because that is the state in which it occurs naturally. Yes, I'm happy somebody is writing attendance submitted. For those who are having challenges, it must be due to your network. I can't explain state function again. It's on slide 3. Please go back and read it. And I've explained it again and again. The last example, yes, you can always go back there. Thank you. My time is up. You have even overstayed. But I advise you, students, to tell your mates the attendance is ridiculously low. I don't know what is happening. I thought on Friday you stayed away because you thought your test will hold, but now you are still not in class. This is not good for your academics. You are freshers, and we are here to teach you and ensure that you have the best academic experience. Please make yourselves available. Once again, I want to announce that Physics 101 lecture will not hold today. Thank you and have a great day.
Okay. No, I need this. Uh, Good morning, everyone. I believe we are all set for our class this morning, Physics 103. Can I hear your response? Is anyone online for Physics 103? Can I hear your response? Is anyone online for Physics 103? Drop your chat. The class will be starting in 2 minutes' time. It will be just an hour class from 10 a.m. to 11 a.m. Get your writing pad ready and get a comfortable place to sit for the 1 hour class. Okay? Yeah, I can see your response. Yeah, that's good. It's time. So good morning, everyone. I want to welcome us again to Physics 103. That is Physics for Biological Sciences. And today, the aspect we'll be looking at for a week or two, we'll be looking at elasticity. Elasticity. And what is elasticity? Is the ability of an object or material to return to its normal shape after being stretched or compressed. We are all used to what we normally call rubber band, especially the ladies among us, and also those people that used to uh, deal with money. When we go to bank, you see using rubber band to band some loads of cash together. So it's a normal thing. It's a common thing that we all know. You see that rubber band, you can stretch it, but once you remove the force, it goes back to its original shape and size. So such property is what we refer to as elasticity. And in in practice, this so sorry for the break. Now, in practice, this property of material is very, very important, even to people in biological sciences, because the materials are, all material are always subjected to forces, and the response of material to forces is very, very important. So in this session, we'll be covering these three topics. The elasticity. We'll be also looking at Hooke's and Erasmus-Young's laws, and also we'll be looking at shear and bulk moduli. These are the three topics we'll be looking at. By the way of introduction, in practice, just as I've said, materials are bound to deform. But ideally, we normally view material as if they are rigid bodies. That is, we normally think the body materials will always maintain their shape and size and do not change under the action of forces. This assumption at times look as if it is true, but it is not. So materials in a real world, all material are deformable to a certain extent when they are subjected to force. So a deformable solid is a body whose shape and or size changes when subjected to external forces. And at times, body also respond to deformation when it is subjected to temperature change. The study of deformable solid is therefore essential to understand how material behave under the influence of a force. So you see, so when we talk of deformable solids, there are key things we should be aware of. The first thing is the external force. And the external force is actually the one that causes the deformation. External force are force applied to a body from its surroundings. When such force act on a solid, they tend to change its shape, size, or both. At times, it may be the shape that it will change. At times, it will be the both when you apply a force. External force may arise from, for instance, applying load, like pulling. When you pull, like the rubber band I mentioned earlier, when you pull a rubber band, it changes the shape and also change the size of the rubber band. The force can also be the external force can also be in form of pushing. It can be in form of contact forces, like so when these forces act on an object, it at times leads to the formation of the body. Depending on how the force is applied, there are different types of deformation that can occur. Number one, tension. That is when you pull. One of the deformation that can happen is tension. That is, you stretch, like the rubber band, you stretch it. So stretching. We can also have a deformation in form of compression. You know, some of us, when we buy bread, a long loaf bread, we want to compress it in order for it to maybe enter your bag. When you apply the force, you compress it. But funny enough, bread does not have the capability to return back to its normal shape. So now it can be in form of compression. It can be in form of shear. When you apply force on a surface, on an area surface, it can be in form of sliding of layers. The deformation can come in form of bending. At times, many of us who've done that before, they have something that is straight, and because you just want to do something, you bend that thing, you deform the shape of that thing. So these are the form through which the formation can happen. So when a deformable solid is subjected to external force, for those objects that have that ability, that property of elasticity, what happens is that the internal force within that material is developed in such a way to return the material or the object back to its original shape. So that force that is developed within the material or the object is what is responsible in returning the object back to its original shape and its original size. So now we have two forces now. The external force that causes the deformation, and also we have the what? The internal force that what? That resists the deformation. That is, that restore the material, the object back to its original shape. I believe we are getting my point. If there's any issue, please let me know at the comment section. Drop your, if I join the lecture and you are getting it clear, please just comment. And if there's any issue, comment, let us know what is happening at your own end. So there are two issues now that we have mentioned. The issue of external force that is applied to change the shape and the size, or the size, and the issue of the internal force that resists deformation, that restore the material back to its original shape. So when the formable subject is, so the internal force developed within the material, this internal force arises from interaction between the atoms and molecules of the material and had to resist the applied the external force. Therefore, the internal force are responsible for one. The internal force are responsible for one, maintaining the structural integrity of the material. Maintaining the structural integrity of the material. Let me see. Someone is just asking that what is the topic? I think you just join now. We are on physics 103, and the topic we are treating is elasticity. And I think you get that clear. Thank you for responding to that question. Okay, let's move ahead. Now, the internal force are responsible for one, maintaining the structural integrity of the material. Because before a material can be deformed, you need to overcome the internal forces of the material. Number two, responsibility of the internal forces is to restore the body to its original shape when the force is removed. When the force is removed. So when you, for instance, that rubber band we mentioned, when you apply for, you stretch it. Of course, for you to stretch the rubber band, you need to apply a force. And what happens is that there's an internal force within the rubber band that wants to maintain its original shape. So you need to first overcome that force, and that's the internal force. So that internal force is what first resists you from that rubber band to be stretched. So you need to overcome that force. So when you remove the force, the internal force will now restore the body to its original shape. Now, the third thing that the internal forces are responsible for is that they determine whether the material failed, fractured, or permanently deformed. There are times you stretch a thing, in the course of stretching it will just tear off. It tear off, that means it failed. At times you stretch a thing, it will just crack in. Or some, you stretch a thing at a time, and you discover that by the time you remove the force, it will be permanently deformed. So the amount of internal force in the material determine whether the material will fail, fracture, or it will be permanently deformed. So now you may want to ask that what's our business as a medical scientist Some of us are medicine students. Some are in biological courses like microbiology. I believe we are here. Some of us will be asking, what's my business with this, with the course I'm doing? Let me just pass this thing and go. It's not like that. Even your profession, that's the reason why school is introducing this topic, this course for you in medical and biological sciences. Even your profession, you need to have the understanding of this topic, because where you are, whatever you are dealing with, even human body will respond to these properties. For instance, there's a structural protein in the body that is normally found in the collective tissue of the body called elastin. elastin. That elastin is the structural protein that gives the collective tissue the ability to stretch and to return back to the original shape. It gives those collective tissues to stretch and to return back to their original shape. And that is elasticity. The elastin we are talking about allows tissues to stretch like a rubber band, and snap back when the stretching force is removed. We won't be able to work without this property of the body part. Now, I think we should take our first code, the first code for our attendance. Let's take our first code. Someone is asking that, what about objects like footballs? Can they also be deformed when it is not punctured? Yeah, when you kick a ball, at the point where you kick that ball, there will be a certain deformation depending on the force with which the ball had been kicked. But because of the pressure inside the ball, as it travels after the kick, it returns back to its original. Shape. So it's possible. It's possible. It's possible. Now, let's take the first code for your attendance for today. Please listen attentively. The code is 5 character. I'm calling, please. 4 H K U 2. I take it again, please. I take it again. The code is 4 H K U 2. Please give us few seconds to load the code. The first code is 4 H K U 2. Thank you so much for that person. The arrow, thank you. But H K U, they are in capital letter. Thank you. So please enter the code. Enter the code and let's continue with our class. Someone is asking, sir, what of the pharmacy? Did they also need this course? Of course, you need the knowledge of this course, because along the way, in the course of your profession, in the course of your training, you'll be dealing with material. Anyone that has to deal with material, objects, your tube, your something, when you are producing some of your drugs, you heat up the tube, the test tube, you need to have the understanding of these properties of this material so that you won't have to stretch the material beyond the normal. So every one of you either in pharmacy, medicine, nursing, other biological sciences, you need the knowledge of this particular topic. Now, as I was saying, I was talking about the elastin, which is a structural protein found in the collective tissue that gives our body, the part of our body, the ability to stretch and return to their original shape. And this is one of the reasons why you and I can walk. If you are walking, you discover that when you are walking at a point, some part of your tissue will stretch and while some will be relaxed. And that's how, and when it relax, those ones that are stretched, they return back to their normal shape. These are the function of this elastin in our body. Where can we find elastin? They are abundant in some of our body, like our skin. Our skin. It allows our skin to stretch. It's also found in abundance in our lungs. The expansion and recall of our breathing that make our breathing possible is by the elasticity property of the lungs. So if the lungs is stiff, there's no way you can breathe. Also in our arteries and blood vessels, even in the heart, these structural proteins are found there. And these are the material part of the body that exhibit this property, the ability to stretch and also return back to its original shape. Look at this day-to-day experience: bending the hand, stretching the skin, which we normally do at times, jumping, involving this. All this activity involves elastic deformation of body tissue. So elastins allows tissues to stretch and return to normal. So when elastin is lacking in the body, what happens? It comes with a lot of problems when elastin is lacking in the body. The first thing that is noticeable is that the tissue will lose elasticity, and that's why you see some people body, they are so you see that their body, their skin is loose, so that it's not firm as it should be. That is, the skin will be sagging. We have sagging skin. Also, if it is lacking in the arteries or the blood vessels, you see the blood vessels stiff, and such things is what normally cause high blood pressure. And also at times when it is lacking in some breathing system, organ of the body, you see the breathing will be difficult. These are the area of the part of the body. It's just an example where you can see the application or the relevancy of the elasticity as a topic that we are talking about. I believe we have entered our code. Someone is asking that I've not changed the slide. Yeah, I've not. I will change the slide, but I'm still talking to what is before us. So I'm still talking to what is before us. Now, I've talked about the external force that cause deformation, that is change in shape or size. And I've also talked about the internal forces that resist deformation and restore the body back to its original shape and size. Now, and I'm now telling us what is the relevancy of these to you as a medicine student, pharmacy and biological sciences. So that's what, and if I may ask you a question now, I may ask us, why does woman's skin return to its original shape after being stretched? Please get the question. Why does woman's skin return to its original shape after being stretched? Why does the woman's skin return to its original shape after being stretched? Now, the fourth point on this slide that we need to talk about is the key concept of the stress and strain. Stress and strain. In the study of the deformable solids, the most important concept that describe how material respond to forces are stress and strain. These are two parameters that describe how material respond to deformation, stress and strain. This concept explain why material deform. This concept explain why materials deform and how much they are deformed when forces are applied. I want you to get this clear. Key concept that we use to describe how material respond to forces are stress and strain. And the concept explain why material deformed and how much they are deformed when forces are applied. So the first parameter is stress. 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 What is stress? Stress can be basically defined as external force per unit cross-sectional area. External force per unit cross-sectional areas. So when you have a material, an object, and you know the area, and there's a force, external force that is applied to it. So you can calculate the stress the material has gone through or is going through if the force is still on the material. And it's just to put the force over the cross-sectional area of that material. And the unit is Newton per meter square. Newton per meter square. Nowhere that force, the unit for force is Newton, while the area is meter square. So when you are giving a question and they give you parameters in form of other things that does not come directly. It does not come directly, like for instance, in a question, you can be given the length and breadth of a material. So, and they give you a force and apply to that material, and they are asking for the stress. So it is your duty to use those parameters to calculate the area, the cross-sectional area of that material. Then, of course, put it under the force. You get the stress. So you need to be careful. And if you are giving the parameter, you be mindful that it is in the correct unit. Be careful that it's correct unit. So we have types of stress, which we will still come across in the course of this teaching. We have the tensile stress, and this is caused by pulling. When you pull something and it's elongated, it increase in size. It increase in size. Such stress is what we call tension stress. We have compressive stress. When you push, when a force cause shortening of a material that you compress it in, such a material go through what we refer to as compressive stress. And we also have shear stress, which is caused by when forces are acting parallel to the surface of the material. And what is the physical meaning of stress? The physical meaning of stress is that stress tells us how strong the material in resisting deformation internally. It tells us how strong a material in resisting deformation internally. The second parameter is strain. What is strain? Strain is the measure of deformation. To what extent a material is deformed, that is strain. It is defined as a change in dimension divided by the original dimension. Change in dimension divided by the original dimension. That is strain. So this is strain. Strain is change in dimension over the original dimension. And strain is dimensionless, that is, does not have unit, because the change in dimension, of course, it will be in meter, and the unit to the original length also will be in meter. So at the end of the day, you have the strain is dimensionless, and it's a measure of degree of deformation. It's a measure of degree of deformation. I would love to call the second attendant code. The second attendant code for today. The second attendant code for today. Please listen attentively. 7 F X A Y. 7 F X A Y. Yeah, thank you. That's it. That's the second code for today. Thank you. Salahuddin Muhyiddin, thank you for that. Yeah. Okay. Now strain is measure of degree of deformation. It's a measure of degree of deformation. Type of strain, we have type of strain depending on the deformation respond to that force. Number one, we have longitudinal strain. Longitudinal strain, changing in length when you subject a material to elongation, it change in length. So we have longitudinal strain, we have lateral strain, change in width or thickness. Lateral strain, we have shear strain, angular deformation. We have a volumetric strain, that is change in volume when a material is subjected to a force. There will be change in volume. So the physical meaning or strain is to tell us how much deformation has occurred. How much deformation has occurred. So from the slides we have covered, from the topic we have covered these two slides, and I would love we lay our hand on some example. I throw a question to us. I say, why does woman's skin return to its original shape after being stretched? I believe if you've been following the explanation, you should be able to respond to that question. Now, I would love we do some example at your hand, and I would love to see your response at the chatting session. Now, today is just like introduction to the topic. So we've talked about the elasticity. What is elasticity all about? And we've mentioned some key thing about elasticity that is very, very important. That is, we've mentioned the issue of external force that cause deformation. So today is just like introduction to the topic. So we've mentioned the issue of external forces that cause deformation. And deformation can either be change in shape or change in size, or the both. And also we have also seen that material also, in one way or the other, they have internal forces within them to resist the deformation. So in such doing, they intend to maintain their original shape. But if deformation take place, it is the responsibility of the internal forces to restore back the material back to its original shape and size if the external force is removed. And also, we have also talked about these key concepts, that is the stress and the strain, which is the force per unit cross-section area. And he make us to understand the degree of deformation. He make us to understand how material respond. That is the implication of stress. It make us to understand how much the material is deformed. And then we now have the strain. The strain help us to measure the degree of deformation, and which is the change in dimension divided by the original dimension. Now, let's look at this question. Let's look at this example based on the introductory class that we have today. Let's look at an object. Please put it down. Put your question down. An object which with an object of 10 centimeter long and 5 centimeter wide was subjected to a force of 100 Newton. If the material, the object, sorry, if the object extends by 0.2 centimeter, what? One, calculate one, the stress. Two, can you calculate the stress? Okay, let's calculate the stress now. Let's first calculate the stress on that material. Did you get the question, please? Let's take the question again. An object of 10 centimeter. Thank you so much. Salaudin, you are following. Thank you so much for that. Yes, thank you. Please, can we calculate and let me see your question, please. Let me see your response. Can we do that in time? What's the stress? Yeah. Miliki, Mayowa, but know that you didn't put the unit. You said 2, but you didn't put the unit. Okay, you later put the unit. Okay, Shola, Michael, you didn't put the unit. What's the stress? Be careful. This is one. This is very, very important in physics. Any calculation, it has a specific unit. So that's why any definition of any formula, there will always be unit there. Thank you, Michael. Okay. So what is the strength? But I want to tell us that some of you that are saying is 2, I think, hope the dimension of the material of the object is given to us in centimeter. You need to convert to meter. So I don't think some of you that are saying is 2 Newton per meter, are you sure that you convert the centimeter to meter? Yeah, Adebayo Ebenezer, thank you for that. I think you convert yours to centimeter. So that's stress. So, but one observation I just want us to be mindful of is that the question, the example I gave to us is in centimeter, the dimensions are in centimeter, the length is in 10 centimeter, while the y is in 5 centimeters. So make sure you convert it to meter. Now, the force is already in Newton already. So the next is that we are told that the object was extended by 0.2 centimeter. So what is the strain? Can someone convert that to strain? Thank you, Ade Tommy Manuel. He said convert the centimeter to meter, then multiply. Multiply by what, please? So what is the strain? The second question on this is, what is the strain? What is the strain? We are told that the object extends by 0.2. So what was the strain? Elijah Akinsure. Okay. So the next question, the next one is, what's the strain of the material? Please, can you respond to that? What's the strain of the material? I just want to know you capture the introduction I'm giving us this morning, because it is on this introduction that we are going to build on. And if you didn't get the introduction, this basic part of the subject, the topic, you may find it difficult to flow along by the time we continue in the subject, please. So what is the strain? Can I get your response for that? I think this is simple. You already have the original length. We are told the extent to which it is deformed, which is 0.2 centimeter. So from the definition is strain is deformed dimension over the original dimension. So it's straightforward. Okay, I can see that. Okay. This is not physics 101. It is physics 103, which is physics for biological sciences. This is physics for biological sciences, and it's physics 103, not 101. Someone is asking, is it physics 101? So please, let's take our last attendance code for today, and then submit immediately. Please, let's listen attentively. Take your attendance code, the last attendance code for today, and submit immediately. 4RS8G. 4RS8G. Murudin, can you type it for us? 4RS8G. Yeah, thank you, Salahuddin. Thank you. 4S8G. Please submit immediately. And once you submit and it's successful, please let us know. Can you just say you are okay? So that someone is asking, the length is what? The length is 10 centimeter. Why the object was stressed by 0.2 centimeter. Done, okay? Over underscore 90, done. Please submit, done, okay? Done. Is anyone again that have submitted his or her attendance? Say, what's the final code? The final code is 4RS8G. 4RS8G. Please, okay, submitted, done. Please do that. So by God's grace, our next class will be on Wednesday, the same time, 10 a.m. So I've given us the introductory part of this subject that we are treating, the elasticity. So by Wednesday, by God's grace, we'll be coming to continue, and you have much more example or question to solve together. So please, I'm still waiting for you to submit your attendance, please. Someone is asking for the first code. So you came late then. For HKU2. For HKU2. Be careful, please. To every one of us, this is my first time meeting you on this platform. That's why I'm a bit slow and more careful with us so that we get things right. By Wednesday, I won't be this simple for us. So be careful. You come to the class in time. It's 10 a.m. to 11 a.m. So before 10, you should have logged in and get ready for the class. You are welcome, Balogun. Okay, please, I would love to leave us at this moment. We will meet on Wednesday. Please, it is advised for us to read more on this subject. You know, the slide is live. That's why someone was asking that I'm not moving the slide. The slide as a single slide contains a lot of things. That's why I have to stay on one slide, speaking to one slide. So you think I should be flowing the slide like that? No. So the slide contains a lot of information which I need to speak to. So please, at your own time, try to study more on these subjects, on this particular point that is raised today, so that and solve more examples. So by the time we continue on Wednesday and continue on this topic, elasticity, you find it easy to flow and to go along. And I know at the end of the day, you and I will smile, provided you follow the basic instruction. Like some of us that are coming late now. So we need to start working so that we can smile at the end of the semester. So please, I will leave us to continue solving the example I give to us, and also search for some other textbooks to solve more questions on stress and strain, particularly on what we have just discussed this morning. Thank you. Have a wonderful day. My first time,